सामान्य स्थिति में भी ध्यानस्थ हो जाएं और विशेष करके उस स्थल पर जहां अन्य किसी प्रकार की ध्वनियां आपके पास नहीं पहुंच रही, अर्थात नीरवता की स्थिति से कहते हैं, जहां पूर्ण शांति हो, आप ध्यानस्थ हो, तो आपको अपनी नासिका से स्वर सुनाई देगा। इसीलिए स्वर संधान का पहला केंद्र हमारी नासिका होती है और उसी से जो हमारा श्वास निकलता है उसी को हम स्वर कहते हैं और इस पूरी प्रक्रिया को स्वरोदय कहते हैं। आप जहां कहीं भी हैं, सुन रहे हैं मेरी बात, तो नाक के 2 छिद्र, दाहिने छिद्र से जो स्वर निकलता है उसे सूर्य स्वर कहते हैं और बाएं छिद्र से जो स्वर निकलता है उसे चंद्र स्वर कहते हैं। अगर दोनों से स्वर निकल रहा है, दोनों से श्वसन क्रिया हो रही है, तो इसे सुषुम्ना स्वर कहते हैं। और इन तीनों के आधार पर हम विद्यमान और आगत दोनों का अनुमान कर लेते हैं। यह ज्योतिष से संबंधित है, अभी प्रोफेसर सामल जी इस पर चर्चा भी कर रहे थे, और विज्ञान से संबंधित। ज्योतिष अपने आप में एक गणितीय विज्ञान है जिसमें अनुमान का अंश बहुत ज्यादा कम है और भाष्य का अंश बहुत ज्यादा है। इस श्वसन क्रिया का भी हम इसी तरह से भाष्य करते हैं। हमारे शरीर में एक तरफ ईड़ा नाड़ी है, दूसरे तरफ पिंगला है और बीच में सुषुम्ना है। ईड़ा से सीधा संबंध चंद्र स्वर का होता है, पिंगला से सीधा संबंध सूर्य स्वर का होता है और मध्यस्थ सुषुम्ना से संबंध सुषुम्ना स्वर का होता है। यह स्वर ही हमारे जीवन का आधार होता है। अगर हम इसके बारे में अध्ययन कर लें, इसके बारे में हम साधना कर लें, तो हम बहुत कुछ आगत घटनाओं के विषय में विज्ञ हो सकते हैं और तदनुकूल व्यवहार या आचरण कर सकते हैं, जिससे इस नाद, स्वर, ध्वनि अथवा श्वसन का बोध हो जाता है ध्यान के माध्यम से अथवा गहन अभ्यास के माध्यम से। वह हर मिलने वाले व्यक्ति के बारे में समझ सकता है। इसीलिए यह अनुमान के ऊपर ध्यान शास्त्र कहा जाता है कि अगर आपके पास कोई मिलने आया तो उसकी आवाज से आप पहचान सकते हैं उसका मंतव्य क्या है। पूरे परिवेश में आप इस तरह से समझने की प्रक्रिया को आगे बढ़ा सकते हैं। वस्तुतः यही स्वर जब ध्वनि के रूप में वाणी से निकलता है तो संवाद और संवाद संप्रेषण का माध्यम बन जाता है। इसी से भाषा विकसित होती है और भाषा 2 रूपों में व्यक्त होती है, एक होती है मौखिक और दूसरी होती है लिखित। लेकिन इस स्वर विज्ञान का संबंध मौखिक भाषा से होता है जिसका हम उच्चारण करते हैं। इसलिए इस पूरी प्रक्रिया में, इसके समझ की प्रक्रिया में 3 स्थितियां बनती हैं और तीनों पर हमें विशेष ध्यान देना चाहिए। एक होता है उच्चारण, दूसरा होता है संचरण और तीसरा होता है यांत्रिक। जब हम स्वयं बोल रहे होते हैं तो यह उच्चारण भाव की स्थिति होती है। हमारी वाणी कहाँ तक पहुंचती है, इसमें निहितार्थ क्या है, हम क्या सोच रहे हैं और किसके लिए सोच रहे हैं, अगर हमें इस शास्त्र का बोध है तो हम जान जाएंगे। दूसरी अवस्था होती है संचरण की। संचरण 2 रूपों में होता है। एक तो कहीं बोला गया शब्द मेरे पास तक आता है अथवा मेरे द्वारा बोला गया शब्द कहीं जाता है, तो इसका माध्यम होता है और इसका माध्यम है वाल, और कण होते हैं शब्द में निहित जो जुड़ करके एक स्थान से दूसरे स्थान पर पहुंचते हैं। विज्ञान की भाषा में संभवतः तरंग दैर्घ्य इसको कहा जाता है। इस तरह से हमारी आवाज पहुंचती है। जो तीसरी स्थिति है इसकी, वह है यांत्रिक। हमारी वाणी को पकड़ करके जो कहीं अन्यत्र पहुंचा रहा हो, आकाशवाणी के माध्यम से, अथवा आप हमें स्वयं देख रहे हैं और यांत्रिक माध्यम से हमें सुन भी रहे हैं और हमारी भाषा शैली का आप अनुमान कर रहे होते हैं, तो 3 दशाएं होती हैं इस पूरे स्वर विज्ञान की। उच्चारण किस प्रकार का है, पहुंच कैसी है, और इस पहुंच को बढ़ाने, घटाने, सीमित करने या समाप्त करने में यांत्रिक विधान किस तरह से आता है। ये तीनों मिलता है तो शोध, अनुसंधान या रिसर्च का विषय बन जाता है, जिस पर हमें बहुत ज्यादा ध्यान देना चाहिए। इन ध्वनियों की भी 2 शाखाएं होती हैं। एक खंडित ध्वनि होती है और एक अखंडित या खंडेतर ध्वनि होती है। जिसे हम खंड ध्वनि कहते हैं वह खंडित नहीं होती, वह अंश में होती है। और जिसे हम खंडेतर ध्वनि कहते हैं वह खंडित भी होती है और अव्यक्त भी हो जाती है। इसका हम मूल्यांकन यांत्रिक विधा से करते हैं। लेकिन जिसमें अस्थायित्व है उसे खंड ध्वनि कहते हैं। अ, ई, क, ख इस तरह से जो ध्वनियां चलती हैं बहुत देर तक रह जाती हैं। हम इसे कि हमारे द्वारा जो कुछ भी बोला जाता है वो हमेशा रहता है, शब्द क्षरित नहीं होते और हमारी आवाज कभी समाप्त नहीं होती। इसीलिए हमारे यहाँ विधान है कि आप बोलने से पहले विचार करिए। वाणी तो अनमोल है, जो कोई बोले जान, ये तराजू तौलिए तब मुख बाहर आन। यह अनमोल है, इसकी कीमत नहीं लगाई जा सकती। पहले हृदय में विचार करिए, फिर वाणी से इसे व्यक्त करिए। इतनी इसकी मान्यताएं होती हैं, तब जाकर जो स्वरोदय है, स्वर विज्ञान है, ध्वनि विज्ञान है, इसका हम निश्चित रूप से अध्ययन कर पाते हैं। और आज के संदर्भ में ध्वनियां दो फलक पर दो रूपों में दिखलाई देती है। एक होती है अघोष और एक होती है सघोष। कभी कभी हम मन में मंत्र का उच्चारण कर लेते हैं लेकिन ध्वनि निकलती है। जैसे नासिका से जो श्वसन क्रिया होती है, आप एकांत में बैठकर ध्यान लगाएं तो आपको श्वास पता चल जाएगा। अगर वो कान से नहीं पता चलता है तो आप उसके सामने हाथ लगाइए, हथेली से आपको उसका नाद पता चल जाता है। तो जब हम मंत्रस्थ होते हैं तो यह ध्वनि हमारी अघोष होती है। चिंतन और मनन दोनों की प्रक्रिया में हमारी ध्वनि निकल रही होती है। इसलिए आप देखते हैं हम कहीं बैठकर ओम का उच्चारण कर रहे हैं, मन में कर रहे हैं, श्वसन में कर रहे हैं, इसकी आवाज दूर तक जाती है। दूसरा इसका स्वरूप है सघोष। जो इस समय आप हमें सुन रहे हैं, यह ध्वनि का सघोष स्वरूप है, जिसमें तेजी से स्वर आपके पास तक पहुंच रहा है। यह सघोष ही वातावरण में हलचल उत्पन्न करता है। जो अघोष ध्वनि है यह हलचल नहीं उत्पन्न, यह स्पंदन उत्पन्न करती है। लेकिन सघोष ध्वनि यह हलचल उत्पन्न करती है। हलचल बहुधा अच्छा नहीं, लेकिन सघोष की पहुंच होती है और अघोष की अनुभूति होती है। इसका हमें ध्यान रखना चाहिए। और इसी आधार पर जो हमारी वाणी है, हमारी आवाज है, हमारी ध्वनि है, यह कभी अल्प प्राण होती है और कभी महाप्राण होती है। जब हम अपनी बात कह लेते हैं और हमारे परिवेश से ही संबंधित रहती है तो इसका असर होता है कि यह अल्प प्राण है, एक सीमित परिवेश के लिए है। लेकिन जब हमारी बात दुनिया के लिए होती है, मानवता के लिए होती है, ओंकार जब हम उत्पन्न करते हैं तो उसका पूरे ब्रह्मांड से संबंध होता है, तब हमारी ध्वनि महाप्राण कही जाती है। वही ध्वनियां मायने रखती हैं जो महाप्राण होती हैं। और महाप्राण ध्वनियां हमेशा और हमेशा कल्याण के लिए होती हैं। उन्हीं के लिए सत्यम शिवम सुंदरम शब्द का प्रयोग किया जाता है। आज के संदर्भों में इसको लेकर बहुत ज्यादा चिंतन हो रहा है, अध्ययन हो रहा है और विशेष करके अनुसंधान हो रहा है। कारण मैंने आरंभ में ही कहा कि इसका संबंध सुव्यवस्था से तथा समानांतर चले तो कानून व्यवस्था से होता है। सुव्यवस्था चिंतन मनन की दुनिया का होता है, जहां केवल सबके हित की बात होती है, आत्मोन्नति और सर्वोन्नति की बात होती है। जब कानून व्यवस्था के संदर्भ में हम आते हैं तो इसमें समाज के उन्नयन और हित की बात होती है, लेकिन जो समाज और राष्ट्र विरोधी शक्तियां हैं उनके परीक्षण की बात होती है और उनके लिए अलग से व्यवस्था विधान करती है। और इसी में फोरेंसिक साइंस का विकास हुआ। अपराधियों को पकड़ने के लिए यह फोरेंसिक साइंस आजकल बहुत ज्यादा चर्चा में है। सारे विश्वविद्यालयों में इसमें प्रयोगशालाएं बननी हैं, कई जगह है भी। जहां भी पुलिस तंत्र है वहां फोरेंसिक साइंस का सहयोग लिया जाता है, क्योंकि हम मनुष्य के स्वभाव को उसकी आवाज से पहचान सकते हैं। इसलिए फोरेंसिक साइंस आज इस संदर्भ में ज्यादा उपादेय हो गया है। और आजकल आप लोग भी सुनते होंगे कहीं फोन टेपिंग हो रही है अथवा अपराधी की भाषा शैली कैसी है, उसके आधार पर भी हम उसकी पहचान करते हैं। सब जगह आजकल जो कैमरे लगे हुए हैं उसके माध्यम से भी बहुत सारी जानकारियां हो जाती हैं। कैमरे व्यक्ति को सतर्क भी कर देते हैं, सावधान आप कैमरे की जद में हैं। अर्थात आप अगर कुछ बोल रहे हैं तो उसका कहीं अंकन हो रहा है और इस अंकन के आधार पर आपका मूल्यांकन भी होगा, परीक्षण भी होगा और आपके बारे में जानकारियां भी मिल जाएंगी। जब हम फोरेंसिक और लीगल एस्पेक्ट देखते हैं तो उसमें ध्वनि अथवा स्वर के कुछ खास पहलू पर विचार करते हैं। पहली जो उसकी मान्यता है उसके अध्ययन की, कि उस स्वर की आवृत्ति कैसी है और इस आवृत्ति के आधार पर अर्थात कितने शब्दों में वह भाष्य है जो व्यक्ति कहना चाहता है और कितने सीमित अथवा असीमित रूप से अपनी बात कहा जाता है, इसे आवृत्ति कहते हैं। दूसरा, अवधि, कितनी देर तक वह बोला, या कम समय में उसने अपनी ढेर सारी बातें कह दी या ज्यादा समय लिया, बहुत कम कहा, तो इसके आधार पर भी हम उसका परीक्षण कर लेते हैं। दो और हैं जो ज्यादा मायने रखते हैं, आरोह और अवरोह। उसके बोलने में चढ़ाई कैसी है, भाषा किस तरह से चल रही है, अथवा एक निश्चित ऊंचाई तक जाने के बाद उसकी भाषा का स्वर किस तरह से घट रहा है, हम इसका भी अध्ययन करते हैं फोरेंसिक साइंस में। और इसका लीगल एक एस्पेक्ट होता है। इसके आधार पर वह अपराधी जो दिख नहीं रहा, अगर अपराधी है तो जिस पर हम अध्ययन कर रहे हैं, उसकी आवाज से हम उसकी पहचान कर लेते हैं। कभी कभी अपराधी नहीं भी हो, किसी विशेष प्रसंग में वार्तालाप हो रहा हो, आजकल फोन टेपिंग का बहुत विधान है, आप सब इससे बहुत ज्यादा अवगत भी हैं, यह सब बार बार अखबारों में आता है। अमेरिका में एक बहुत बड़ी घटना भी हो गई थी इसको लेकर के, वाटरगेट स्कैंडल जिसे कहा जाता था। तो अब इस माध्यम से भी अगर कहीं दो व्यक्तियों का संवाद टेप किया जा रहा है, उसके माध्यम पर मंतव्य स्पष्ट होता है तो उस संवाद का ध्येय क्या है, क्या वह गुप्तचरी के लिए है अथवा क्या भविष्य में किए जाने वाले किसी अपराध के लिए है, अथवा अपराध हो गया है तो उसकी जानकारी देने के लिए है। इन सारी चीजों का अध्ययन, सारी बातों का अध्ययन हम फोरेंसिक साइंस में करते हैं और फिर तब एक लीगल प्रोसीजर आरंभ करते हैं कि अगर इसमें कहीं अपराध बनता है तो अपराधी तक पहुंच हो जाए, अपराध नहीं है तो इसका कोई अर्थ नहीं होता। कभी कभी व्यक्ति का स्वभाव जानने के लिए भी हम नाद स्वर का अध्ययन करते हैं। आजकल जो हमारा ज्योतिष विज्ञान विकसित हो रहा है, पहले से बहुत ज्यादा विकसित है, आज के संदर्भों में हम जो प्रयोग कर रहे हैं इसमें शब्द और ध्वनि के माध्यम से व्यक्ति के स्वभाव और भविष्य की जानकारी करते हैं कि अगर व्यक्ति मधुर बोलता है तो भावना प्रधान होगा, व्यक्ति मधुर नहीं बोलता है तो उसके अंदर कहीं ना कहीं आक्रोश का भाव निहित होगा। इसका आशय ये नहीं कि सभी में ऐसा होता है, ये कुछ विशेष संदर्भों में इस प्रकार के अध्ययन हुए हैं और उसके ऐसे निष्कर्ष माने जाते हैं। व्यक्ति के लिए जैसे देखने से पता चल जाता है, फेस इज द इंडेक्स ऑफ माइंड। आप किसी व्यक्ति का चेहरा देखिए तो उसके मस्तिष्क में क्या चल रहा है इसका थोड़ा थोड़ा अनुमान हो जाता है, और उसकी वाणी सुनिए, उसकी आवाज सुनिए तो इससे पता चल जाता है कि उसके मन में क्या है और उसके भविष्य की दिशा क्या है। केवल मनुष्य से संबंधित ध्वनियों का मायने नहीं है, आप पक्षियों की आवाज से भी आगत घटनाओं का बोध कर सकते हैं। जो जीव जंतु वन में संचरण करते हैं उनकी आवाज से आप पहचान कर सकते हैं। प्राचीन काल में हम जिस अंचल में हैं वहां सूचना तंत्र ध्वनियों के माध्यम से चलता था, इसलिए ध्वनियों के संकेत होते हैं। ध्वनि विज्ञान उन संकेतों का भी अध्ययन करता है। नगाड़े से ध्वनि निकल रही है तो उसका आशय क्या है, बांसुरी से निकल रही है उसका आशय क्या है, धनुष का टंकार है इसका आशय क्या है। तो इस तरह से हम ध्वनियों से बहुत कुछ समझते हैं। आप आसमान में बिजली की आवाज सुन करके अनुमान कर सकते हैं कि बादल किस तरफ होगा और बरसात कितनी देर बाद हो सकती है। तो इसके आधार पर हम ध्वनि शास्त्र के आधार पर बहुत सारी बातें समझ सकते हैं। मनुष्य का मंतव्य और गंतव्य, एक समाज की दिशा और दशा तथा प्रकृति में होने वाले घटनाक्रम, इन सब का अनुमान हम ध्वनि विज्ञान के माध्यम से कर सकते हैं। समाज की व्यवस्था बनाए रखने के लिए इसकी जानकारी आवश्यक है। शासन को सुव्यवस्थित करने के लिए इसकी जानकारी आवश्यक है। और इसलिए कभी कभी मौन मुखरित भाषा से भी ज्यादा मुखर होता है, क्योंकि मौन की अवस्था में ध्वनि तरंगे ज्यादा तेजी से निकलती हैं बनस्पत उच्चारण के माध्यम से। इसलिए संचरण हो, उच्चारण हो अथवा यांत्रिक विधान हो, सभी को जब मिलाते हैं तो यह शास्त्र पूर्ण होता है। आज तकनीकी का युग है, तकनीकी कौशल का युग है, इसलिए हम इस यांत्रिक विधान का विशेष आश्रय लेते हैं। हमारा आपसे संवाद भी इस यांत्रिक माध्यम से हो रहा है, जिसे डिजिटल प्लेटफॉर्म कहते हैं। अब इस प्लेटफॉर्म पर असीमित सूचनाएं, असीमित शब्द, असीमित स्वर और असीमित ध्वनियां अंकित हो सकती हैं, और इनके वर्गीकरण, परीक्षण और पुनरीक्षण के माध्यम से हम बहुत कुछ समझ सकते हैं। इसलिए आवश्यक है कि आज हम फोनेटिक और फोनोलॉजिकल रिसर्च के बारे में ज्यादा ध्यान दें और इसके बारे में भविष्य की दिशा निर्धारित करें। दिशा अच्छे के लिए, अच्छों के लिए, सतत अच्छाई के लिए, और इसे हम पुनः सतत विकास का माध्यम बनाएं। पुरुष प्रकृति के संबंधों को हम बेहतर रूप से व्यक्त करें, संतुलित करें और व्यवस्थित करें, और इस क्रम में हम अपने राष्ट्र को स्वच्छ, स्वस्थ, समर्थ, संपन्न, समृद्ध और आधुनिक संदर्भों में महानतम राष्ट्र बनाएं। आप लोगों ने एक गूढ़ विषय पर वेबिनार का आयोजन किया है, इसके लिए आप लोगों को बधाई और आप सभी के लिए ढेर सारी शुभकामनाएं। बहुत बहुत धन्यवाद।
Thank you, sir, for that very insightful.
बोलना इस समय था और आप इस
So we shall now move on to the technical session. I would, before that, I have a small request to all the participants. Please do not click on present button. Kindly mute your mics and turn off your videos for the smooth contact of the webinar. Okay, now I would like to introduce our first speaker of the day, Dr. Shushandu Saman, Head Center for Studies in Linguistics, Bandar Lampung University, Indonesia. He's a lecturer at English Education Department, Bandar Lampung University. He is also the founder and president of Indonesian Community for Forensic Linguistics. He has been a Fulbright Senior Research Fellow at the Department of Cognitive Sciences, MIT, USA. He was also a postdoctoral research fellow in forensic linguistics at Shanghai Jiaotong University, China. He has completed his PhD in linguistics and phonetics from English and Foreign Languages University, Hyderabad, India. He has completed 3 projects funded by the Indonesian Ministry of Research and Higher Education. His research interests include forensic linguistics, neurolinguistics, systemic functional linguistics, systemic phonology, acoustic phonetics, forensic phonetics, and acoustics, to name a few. I welcome Dr. Shushandu Saman to deliver his lecture. Over to you, Shushandu.
Yes. Good afternoon. Namaste. Warm greeting from Indonesia to all of you. Would like to share my PowerPoint here. Okay, just a minute. So, is it visible from there?
Yes, yes, it is visible.
Okay, I should start from the beginning. Yeah. All right. Good afternoon to all of you. Very warm greeting from here, Indonesia. I'm presenting my topic from my home because right now working from home as the policy from the university. So for some reason, for health the reasons I cannot go to the university to present the talk. So from here, the topic that I will deliver is forensic phonetic for law enforcement. Special thanks for the invitation, Dr. Anusri, my colleague. She's also graduation from the EFL University. For this topic, it is very challenging for me, especially because right now I'm still working on the project funded by the government of Indonesia, and then also some projects collaborated in collaboration with some colleagues in Indonesia and other countries. Next, small introduction. Which has been introduced by Dr. Anusri. So in 2018, I was in MIT doing forensic linguistics, especially for the integration of forensic phonetic with the mechanic system of lie detection using functional magnetic resonance imaging. It is a kind of technological infrastructure to get the activity of the brain. So at the same time, I'm looking at what happened with the brain activities while the people are stimulated with some questions to find out some information which are required for, let's say, for the criminal investigation and so on and so forth. And doing postdoc for 2 years and a half in China, also doing the forensic linguistics for several cases in China, for corruption cases and then murder cases, and then what else? The economic cases, for the conflict of the trade. And a little bit about what I have been doing, because it is very much related with the thing that I will be discussing in this seminar, about how we are trying to look at the sounds, the analysis of the sounds in the forensic setting. So in MIT, I propose some research questions regarding how we utilize the knowledge of the phonetic, the knowledge of the language analysis in terms of sound, how the sound is produced, how the sound is transferred, how the sound is perceived, and many things regarding about the sounds related with the mechanism of the lie detection using the fMRI as the research equipment in the laboratory, in the brain, in the Department of Brain and Cognitive Sciences at MIT. Very nice. And for forensic linguistics itself, we here in the university in Indonesia, working at the Center for Studies in Linguistics, forensic linguistics is one of the topics that we are welcoming for collaboration, not only within the university, but also out of the university, out of the country, Indonesia. So we welcome for those who are very much interested in this topic: language acquisition, learning and teaching, technology, typology, bio-linguistic, forensic linguistic. Yep. And in special for forensic linguistic, we are looking at the language science as the application, the application of language science in forensic settings. One of them is language and law. We are looking at the correlation between language and then law, and then language in the police investigation, and then language in the court. So we take the data in the courtroom, and then speaker and author identification. We look at the the data of in the spoken and written channel, and then try to analyze, and then try to find out who is the speaker of the recording, and then who is the writer of the writing. And then also for lie detection, and then forensic stylometrics, we are looking at the handwriting, and then forensic phonetics that we are going to discuss, and then automatic speaker recognition, cybercrime and terrorism, and many other things related to the application of the language science in forensic setting. Yes, for forensic linguistics, there are some courses that I have been teaching. This is one of the class that I have been involved to teach the classroom. So the students are police officers in the computer department. So I was teaching 2 semesters for forensic linguistics. So we are looking at the cases that they face in the field regarding about the crime investigation, when the evidence are related to the let's say to the recording or to the handwriting or to the notes, whatever, which when we can apply the language science into the analysis of the evidence of the crime. And also, once we are dealing with the forensic phonetic, if you are very much interested doing that kind of thing, apply the language science into the forensic setting. So we must be aware of the connection with other dimension of the university in the society, that is the police department. So we in Indonesia, I visited many places regarding about the infrastructure that can be used, because in the university sometimes we have a limitation to analyze. To get the data, to analyze the data, something like that, as regarding about the tools. So visited. This is the forensic laboratory belong to the police department. This is in Bali, and then this is in North Sumatra, Medan. And also we introduced how the language science can be used to help police department, especially for, this is a kind of seminars for cyber crime. Yeah, so I introduced the methodology of the language science and how it can be utilized in their system. Yeah. Also, we promote the subject of English, because it is quite new in Indonesia. So not all students are brave enough, confident enough to take the forensic linguistic or forensic phonetic as their first, let's say, thesis or dissertation. So this is two dissertation, doctoral dissertation I supervised. The first language, the language of open trial in district court, and then an acoustic phonetic study in forensic linguistics. Mr. Sabriandi Adrian take the data of the corruption cases in his area, in his city. And then also there is another, the other one, the reality construction and forensic discourse of police investigation report. She's Sharma Panggabean, take the data of the police interrogation in her place. Now, in talking about forensic phonetics, so we can also look at above forensic linguistics. So we are talking about language, law, crime, the interface between language, law, and crime. So we are not talking about the language itself, but we are talking about the law, we are talking about the crime, and we are talking about the whole thing all together. So once we are dealing with forensic linguistics, forensic phonetics, we cannot be apart. We should look at some references in law and then criminology. Now, looking at forensic phonetic, and then try to understand what is being discussed for law enforcement in forensic phonetics. Still, we start with speech production, speech acoustic, and speech perception. It is a very common thing that we are studying for forensic for phonetics. Now we are trying to utilize this kind of knowledge in phonetics for the production, acoustic, and perception, and then try to utilize these, look at this into the forensic setting. It is a very small video to look at how actually the phonetic can be utilized in the crime investigation. Please allow me to play this small video for all of us.
My name is Cindy Bristow. 7 years ago, I was recruited by a secret branch of the CIA called ST6. I was sworn to secrecy, but I couldn't keep it from my fiancé. And when the head of ST6 found out, he had him killed. That's when I learned the truth. ST6 is not part of the CIA. I've been working for the very people I thought I was fighting against. So I went to the only place that could help me take them down. Now I'm a double agent for the CIA, where my handler is a man named Michael Vaughn.
Hear that? What? That pitch? Definitely 9mm. That's a close range hit. Twice in the chest, once in the head.
Yeah, it's exactly how Eloise Kurtz was killed. See, whoever sent me this tape wants me to hear her getting killed. Why in the hell would you want that?
You don't know it's a she. You hear that? That delay before the last one? That's the one in the head.
Hey, can we isolate that?
Yeah, I can definitely improve on it.
See, this tape was made from that time. It was from the body.
So whoever paid that girl to say she was Kate Jones is the same person who gave her the pin, is the same person who sent you the tape.
No, not necessarily. Someone else could have given her the pin. Or replaced the one she already had with the bug. And even if that was the same person, this thing was on a wireless transmitter, so someone else could have made this tape.
Hey, we'll get it somewhere.
Why would someone send the fake Kate Jones and want me to hear this?
You can tell him about ST6.
What was that? Hold on.
You can tell him about ST6. About ST6.
ST6. ST6.
Did you tell him about ST6?
The hell's ST6?
Okay, it is a small clip of the movie regarding how a phonetician can be helping the crime investigation. It is one of the task is about the intelligibility enhancements. Once the data of in the crime investigation. Finding out the exact because the speech sound is not clear enough, then it can be enhanced with the technology. It is one of the tasks of a phonetician to be in forensic phonetic. So these are some features for forensic phonetic that can be used at 0 parameters, the fundamental frequencies, and then the resonance frequency parameters F1, F2, 3, 4, loudness, yeah, the intensity, the source signal, and then the speech rate, the pulse length, also how many pulses in kind of particular data, and then also the deletion, insertion, repair status, and then discrepancies, centralization of vowels, and then the rhythm, prosodic contours, and then formal coupling F1, F2, F3, F4, something like that, and then the syllable grouping and many other things. You can refer to Gold and Friends 2011 and Friends and Steven 2013. So Assigned task in forensic phonetic, in the movie that we just seen is one of them. It is intelligibility and intelligibility enhancement. So one of them, which is very common, is about the speaker recognition. Yeah, speaker recognition can be divided into two: identification and verification. What are the differences? So very basic. The basic difference of the speaker forensic speaker identification and forensic speaker verification. Once it is concerned with establishing the identity of speaker who is a member of potentially unlimited population, then it is a forensic speaker identification. But once we have a given speaker, and then it is in fact the one member of a closed set of speakers which he claims to be during the investigation, then we call it as a forensic speaker verification. And for the forensic speaker providing, once we are dealing with a case, then the phonetician is asked to produce a speaker profile on the basis of the recorded speech, which is being investigated. The information may be the criminal sex, or the age group, the regional background, the social background, or even the educational background through the speech which is recorded as the legal evidence. And then also for the our intelligibility enhancement in the video that we just we had just seen, it is undertaken to determine what is said is in evidential recordings rather than to establish the identity of the speaker. So it's different from the forensic speaker identification. And then the work, the task involves the use of digital filtering techniques, the equipment that we just see in the movie, and then it aims to reduce the presence of unwanted noise. So a lot of noise, then we reduce the noise more and more, then we can find the speech clearer and clearer. And then audio tape examination. Here, the task is about we are trying to find out whether the recording is genuine or not, or whether it is edited or not, something like that. So there are some parameters in the mechanism how to find out whether the audio tape or digital tape as the legal evidence is which is being investigated is originated or edited. Nowadays there are many things in Indonesia. There are several cases like that where the video share via WhatsApp or social media, and then but the video are already edited, and then to get then the police trying to find out whether it is original or not. And for the scenarios, there are two. Here I'm talking only for the first one, forensic speaker identification and forensic speaker verification. The first one we can do with the scenario of naive speaker recognition. So here we are not equipped with the software or equipment. So just a naive speaker is assigned to recognize whether it is familiar or unfamiliar. And then the technical, but for the technical speaker recognition using the computer software or other things, for auditory forensic analysis, and then also for computerized analysis using acoustic forensic analysis, or even automatic speaker recognition. So there are many scenarios for this regarding about the forensic speaker identification and forensic speaker verification. So, but the problem, it is quite controversial regarding about how actually the reliability and validity of the analysis provided by a phonetician regarding about the speech recording being investigated. So there are some cases, not only in Indonesia but also other countries, which have been challenged in the courtroom. So let's say if the accuracy is 80%, then the question is how is about the other 20%? It is one of the challenge that we can find we can find in the courtroom. So to avoid that, to get the reliability and validity of the result of the analysis, which presented as the legal evidence analyzing the data. So I propose, we proposed in 2017 for having such kind of system. It is for speaker verification system. So speech signal, we need two kinds of speech signals. The first one is known K, and then the second one is unknown UK. The known one, the known one is the recording from the suspect during the investigation, and then the unknown one, UK, the UK sample is the recording which is being investigated. Then we do pairing. Then pairing, we do tagging. Then tagging, we do acoustic feature extraction. Then statistical analysis. Then present it in the legal evidence. But within this pairing and tagging, we propose some control to make sure that which have been tagged is not misleading. Because if this is problem, then then it is very much problem. And then so this kind of control and then filter for the acoustic feature extraction and then statistical analysis, because everything can be counted, but which one is counted is the problem. So as a phonetician, and then we also get the knowledge of speech production, speech transmission, and then speech perception. So these kind of the two things, control and filter, it is the thing that we can do to get reliable and valid result for the analysis. Then we present it as the legal analysis of the legal evidence. Then how is the dimension of analysis in forensic phonetic? So it is 2018 and 2020 as a book chapter 2020. And then first we have the comparison, the comparison of the data. Earlier we have K and UK samples. It is the comparison, pembanding. We call it in Bahasa Indonesia pembanding comparison. And then we have a differentiation. Which features can be used to differentiate between K and UK? And then it is in the feature extraction. So the feature extraction, the phonetic feature extraction is very much important. Then the third dimension is here we use statistical analysis. We measure calculate to get the inferential result, which one is whether it is spoken by the same speaker, for example, or whether it is spoken by different speaker. It is another example. Yeah. For example, once we are dealing with forensic phonetic in the court procedure, in the court proceedings, it is 2017. So here, this is the case that I analyzed in China. One company has a problem with another company because duplication of the trademark. Then here I analyzed the language of the lawyers and the language of the judge, the language of the prosecutors, and then we get the pattern information focus. Here I'm using the tonic syllable in the intonational phrase. It is one of the analysis. It is from 2014. The analysis of the melody that can be used for phonetic. Then one of the problem in forensic phonetics, it is not all the time smooth ways. So one of the problem is how we measure the results. Yeah, it is 2020. I proposed for forensic phonetics using the artificial neural networks. So the system, it is the thing that I learned from MIT 2018. So using how the brain works and how the computation can be the computation resembles the brain works. So it is very unique. The artificial neural network, we have input here. So whatever parameters that we analyze, let's say we focus on the formal frequency. So here we have F1, F2, F3, F4, for example. Then we have how many hidden layers, and then input. Which input we want to have as the target of the analysis. Then we provided the analysis artificial neural network using software. Forensic phonetics is very large. It is only a small case that we have been discussing just now. Another challenge is how about forensic phonetics in the mechanism of lie detection that I proposed in 2018 in MIT. So how the sounds is integrated, the sound analysis integrated in finding out whether the information is hidden, whether the speaker is telling the truth, or whether the speaker is hiding the truth, something like that. So it is very much challenging for us, for phonetician, for those students who are studying phonetic and phonology. Looking at earlier in using polygraphy, the peripheral neuron, and then using the activity of the brain, using the eye movement, and then using the what we call it. We can identify. The warmth, yeah, the heat in the body. So there are many things. Then we can. It is a great challenge. How is forensic phonetics in the mechanism of lie detection using this kind of thing which are available right now? Yeah. just an example, the first one with the brain activity, yeah, phonology, orthography, and then articulated word, written words, and then the neural system for auditory and visual word repetition, for example. There are many research papers about it. Then it is very good start for us to look at finding out the forensic phonetic in relation to the brain activity. It is kind of motivation for students, also for me, that once we are looking at the phonetic, the application of the language science in terms of sound analysis, phonetic and phonologically, we have to have openness, looking at new ways of designing, because it is new areas. So from theories, so we start from the theories, or even we propose, we find out which one can be used, which one can be elaborated with other things. So, and then the most important thing in my experience is willingness to collaborate. So phonetician in forensic domain, in forensic setting, cannot work himself. So, for example, I look at, I talk a lot with, discuss a lot with lawyers, with neuroscientists, with biologists, with physics, many other things, to get more insights and then to design together. Then, because it is in the context of research, yeah, the current trends in phonetics, and one of them is a forensic phonetic, we must equip with the laboratory experiment, yeah, and then experimental simulation. It is very for students, do not worry about this, because many students come to me asking about the data. If we are trying to analyze forensic phonetic, they are trying to do research in forensic phonetic, because the data are not available, because because you know, belong to the police department, and then it is confidential, something like that. Then we can do as simulation. We create such kind of situation regarding about the data with this particular scenario resembles to other particular case. Then we have it as the experimental simulation. It's okay, because forensic phonetics, the limitation that we have for the analysis is, for the research, is the availability of the data. Then one of the strategy, not only the strategy that we can do, is using experimental simulation. Yeah, it is the fMRI, the room, the control room. So at the same time, we have somebody here get inside into the tube, and then the person, the subject, is stimulated with some sentences on the screen, and then while he responded the sentences, we are looking at what happened in the brain, which part of the brain is active and which part of the brain is not, compared with other. And it is in Bali. Once it is EEG, not fMRI. So EEG is not so complicated with the previous one, fMRI. So it is we are looking at the electric wave in the skull. Then forensic phonetic for law enforcement, we are looking at any possible communication, conversation, the spoken channel, yeah, the spoken channel. Then try to look at the possibility which which kind of area in the phonetic can be utilized. Yeah, speech production, acoustic perception, then present it as the analysis to analyze the legal evidence for law enforcement. It is a little bit more the video. Yeah, for the voice analysis, we can do, audition can do that using photographic analysis. And then we have to match the voice frame. This is spectral analysis. The harmonic frequency.
We have a woman ran in the lobby, so she's been shot. She's laying on the floor in his blood. How old is she? She was about 20. She's in the lobby right now? Yes, ma'am. She just passed out. I have to call in. I think you need to send a police too.
All right, just one more slide. So looking at various languages spoken in India, also in Indonesia, we have many languages spoken in India, right? And then it can be great challenges for us, for students, scholars working with phonetic and phonology, and then dealing with forensic phonetic, to look at more things to elaborate regarding about the forensic phonetic. So those out of our laboratory, phonetic, phonological laboratory, criminal investigation are looking for us to help them. All right, thank you very much. It is the thing that I can present for today's. Hopefully that it can motivate, and then for students, and then also for me myself. Thank you very much. Yes. Okay. Yeah.
Thank you very much, Shushandu, for that interesting segment, forensic phonetics, and telling us what all you've been doing there. Okay. I think we can take some questions. If anybody has any questions, you can ask.
Yeah. Okay.
Does anybody have any question? You can unmute your mic and ask.
Yeah.
Looks like we haven't got any. Okay then. Thank you, Shushandu. Thank you very much. We shall now move on to our next presentation. Okay, so Now let me introduce our next speaker, Dr. Priyanka Sharma. He is Associate Professor, Department of Humanities and Social Sciences, IIT Guwahati. He is actively involved in the Center for Sciences and Technology at IITG. Before joining IITG, he worked in the Department of Linguistics and Cognitive Sciences at the Hankook University of Foreign Studies, South Korea. He has received his PhD in linguistics from University of Florida. Prior to that, he has received his MPhil and MA from CFU Hyderabad. His research interests are in the areas of phonetics and phonology, vowels and tones, Tibetan Roman languages, language technology, development, speech perception, and speech recognition. So, Priyanka, it is a pleasure to have you with us here today. Over to you. Shushandu, it would be good if you can stop your presentation and mute your mic.
Yeah.
Yeah, okay, Priyanka, over to you.
Yeah, Anushree, thanks so much for inviting me here to this webinar. And also thanks to Bapa Susanto for his presentation, because he has made my job a little bit easier. Some of the things that I'm going to talk about, he has given you a preview about that. And I hope I am audible right now. Is it fine?
Yes, it is.
Okay, super. So this is a very minimalistic title, measuring vowels. That is what I'm going to talk about. And this I'm doing it in a very workshop kind of style. So sorry about that. I'm not doing it as a I'm not going to tell you exactly what are the recent trends in phonetic research right now, but I'm going to talk about a few methodologies that we have been using recently to do our own work. So I must warn you that if you're a seasoned speech researcher, if you're an expert in acoustic analysis, if you're a veteran researcher doing vowel analysis, maybe this presentation has nothing new for you. However, if you're a student, which I believe 50% of this crowd is, which is about 70 people right now, maybe this is of some use. And if you want to know something about vowel analysis, probably this may be of use to you. And thirdly, I'm also expecting that if you are a student, then you have some idea about reading waveforms and spectrograms, and you have worked a little bit with Tract in your courses or in your work. So with that assumption, I'll proceed with the next slide, where I'm going to talk about the plan of my talk. I'm going to talk about vowels and their acoustic correlates, which is Bapa Susanto has also talked about a little bit in his presentation. And then I'm going to talk about how to analyze vowel data, a little bit of analysis of vowel data, and then finally how to deal with speaker effects, overlaps, etc. So I thought that because now it's a good time for you to whether you want to decide to stay on the webinar or want to leave the webinar. So I thought that I'll give you some subsections of my talks too. So in the vowels and the acoustic correlates, I'm going to talk about the source filter theory, maybe 5 minutes in total, harmonics, formants, and vowel formants, something that Bapa Susanto has also talked about in his work. So then part 2, I'm going to talk about the recording context that we usually take care of, and then a little bit about data segmentation, how we segment the vowel data, and then how we identify the vowel regions and how we mark the vowel regions. And in part 3, I'm going to talk about extraction of formant values, removing of speaker effects, plotting with vowel data with ellipses, overlap, what kind of overlap measures we can use, and then finally I'll stop at classification. Again, classification also something Bapa Susanto has given some idea about, talking about the deep neural network, etc. I'm not going to such a level, but I'm going to talk to you about a very basic classifier that we all can use. So the first part is the source filter theory, and I want you to first listen to these two sounds. Hopefully you'll be able to hear these two sounds. And this is the first sound is me producing like do re mi fa sol la ti do with or sa re ga ma pa da ni sa in the Indian classical music terms in vowel a form, vowel a. So it sounds somewhat like this. Okay, now what I did is that I tried to simulate that how our vocal cords are actually vibrating. What is the sound that vocal cords are producing when making the same sounds, same like vowel in do re mi fa sol la ti do, and this is what it sounds like. So as you can see here, as far as the vocal cords are considered, you only hear a buzz. But when I add the vocal cord with my vocal tract, then you can hear a very quick, easily discernible, like, a vowel without any problem. So in the first case, where you heard only the pulses or only the, like, this part, this is what you're hearing is that only the vibration of the vocal cords here. And when you have heard the a vowel with the do re mi fa sol la ti do very correctly, very in a very understandable way, what I have done is that I have added the vocal cord information with the vocal tract information, that is the source and the filter information together. So basically, the source filter theory says that speech is a combination of the source vibration, which is the global fold vibration, and the vocal tract is the filter, which results in the speech. And if I look into the spectrograms of the only the source filters, where you have only the buzzes, like somewhat like this, compared to this is the full speech. As you can see on the left side, when I just presented you with the vocal fold vibration, the spectrograms actually look very similar to each other, even though they're compressed a little bit here and there. But there are not much information there. These bands that you will see here, which we call the formants, are more or less the same. So if we look into the formants more carefully using the Pratt analysis, then you'll see that in the first case, when we look into the source characteristics, the formants are not changing much. However, in the second case, where it has come out through the filter, which is our vocal tract, you can see that the formant frequencies are very different from for each vowel. So this is the basis of the of vowel analysis, as you know, and it has been talked about many years ago. In fact, the first there was a letter by Professor C.V. Raman to the Nature journal in 1920s or 30s, I cannot recall it very well, where he has first talked about the relationship between the vocal tract and the vowel production. And later, Frank in 1962 has come up with the idea of a source filter theory, where he says that human speech is a combination of the source signal, which is the vowel fold vibration, and combined with the filtered by the vocal tract. Okay, so then we'll go to quickly to, I'll talk about the F0 harmonics. Again, Bapak Susanto has talked about harmonics in his talk too. So by nature, what happens is that when we have the vocal cord vibration, we produce a particular fundamental frequency, right? The vibration of the vocal cords, if it vibrates 100 times a second, it is 100 hertz, etc. But by nature, each fundamental frequency also has also leads to the creation of some additional frequencies, which we call the harmonics. And there are always going to be the multiples of the fundamental frequency. So if my fundamental frequency of the vocal cord vibration is about 100 hertz, that is 100 times of vibration in a second, the harmonics will be 200, 300, and so on and so forth, 400, and so forth. So we can assume that the fundamental frequency or basic vibration is the first harmonic, and then we go to the second harmonic, H2. It is 2 times the H fundamental frequency, then 3 times the fundamental frequency, etc. However, remember that is what is happening at the source and the filter being a very restricted filter, because in our real speech it is not the case that all the harmonics or all the harmonic frequencies like 200, 300 are actually audible, or they are actually they're audible for the normal hearing population. So what happens is that the filter it stops some of the harmonic frequencies and let other harmonic frequencies come out. So I look at it with this particular diagram. If you look into that there is a light source, and then which we assume that is almost comparable to our vocal cord vibration here. Then we consider our filter, this vocal tract, as a set of as a wall with a set of windows there, which allows some like light to pass through it. However, it stops some other light. So similarly, our vocal tract also, what it does is that some of the harmonic frequencies that you have got, it filters some of them and then dampens them, and some other harmonics, it actually increases the intensity and increases the amplitude and makes them more heard. And so those are basically what we describe as formants. So now what happens is that, as you probably know, that each vowel production, when we produce each vowel, the mouth has one particular, the vocal tract has one particular configuration. If you look closely here, when I'm producing an ah, the mouth is more or less open. And when I'm going to produce a, it goes a bit, the tongue goes a bit higher. And when I produce an E, the tongue goes even further higher and my vocal tract becomes narrow at the front. So this is much better shown using this particular model of the vocal tract in a study on diphthong production. So you can see that the person here, actually, this is a this is the model of the vocal tract here of a person producing iya. Right, so he starts with E at time 0 on the bottommost panel that you can see. As he produces E, you can see the backside is a little bit thicker. The vocal tract is a bit bigger. The front is a bit smaller. And as he proceeds all the way towards A, the front becomes much larger and back becomes much more narrower. Right. Also notice that sometime in between these two extreme configurations, somewhere there, the vocal tract becomes almost like a normal pipe. It's a normal cylindrical kind of shape it gets into. Okay. So based on these characteristics, we have this, we have devised the vowels, separated the vowels into closed, open, that kind of categories, because when we said I is an open vowel, then it means that mouth is open, and then E is closed, and E is its mouth gets narrower. Now, as a result of that, what happens is that the harmonic frequencies that we have talked about, these harmonic frequencies, different harmonic frequencies get filtered differently. In other words, when you are producing, if you look into the analogy of the previous window in a wall picture, what happens is that the windows keep on shifting depending on how you have opened the mouth as A or E. So as a result of that, the passed out frequencies, frequencies that are let out, right, which are the formants that we call, the formants also keep changing. So here is another example of somebody. What they did is that these people tried to configure the vocal tract. They modeled the vocal tract as a glass tube. As you can see here, in the first case, in the A, you can see a glass tube which has a lower, narrower part on the bottom and the wider part on the top. So what they did is that they used a duck called pipe, which sounds somewhat sounds like this. This is used for calling ducks, and they have added this as a source to this pipe and tried to see what happens. Right, here we go. In the first case, as you can see, when we added the duck call to this tube, what happened is that it actually started producing a sound like ah. Similarly, here it is. If we change the glass tube shape, it starts producing an E. So that also tells you that the whole the whole source and filter whole mechanism is actually more or less, it is replicable. We can replicate it. And also, if we replicate it so well, that also means that it is also quantifiable to some extent. So the features, if we can get the formant features of this A and E, we can actually see the distinct formant frequencies for A and E vowels that many of you have probably already come to know. So I'm not going to go through all of this because I think we are already running late on time. But if you look into the second bullet point here and the sub points there, what we know is that the F1 frequency, or the first Forman frequency, is actually inversely proportionate to tongue height. Many of you already know that the higher the tongue goes, F1 becomes lower. F2 is vowel backness, so the more back the vowel is, the less will be the F2. If it is a front vowel, then F2 will be high. So based on that, what we can do is that we can do some acoustic analysis using Tract and other kind of softwares, and we can get this F1 and F2 values, plot it on a plot, and then we can get these unique regions for each vowel. That is what you have probably seen in many different studies and different kind of representations. So this is what it actually looks like. So this is data from one language that we have used. We have used data from 6 speakers speaking the 6 vowels in this language. And what is happening here is that, as you can see, there are like bunches of dots here. For example, for the A category, you can see that these red dots are all over, like in a group together. But they are not exactly, all of them are not overlapping. It's not a single point, right? So this also makes us realize that there is something about these vowels, that even though vowels are categorized into different 6 categories, you can see that there are 6 different categories here indicated by the color. But at the same time, within the category, there is an enormous variation in the vowels. And those variations come because of several reasons, such as where the vowel has occurred. Has it occurred after a consonant, before another vowel, before a consonant? Is it spoken without in a sentence or in isolation? Who spoke that? What was the height of the person, etc., etc. So if you look into the discrete representation of the vowels, as you have seen in this case here, what you notice is that their dots are all over the place. So what we do is that we try to calculate the average of these dots, as you have seen in these different diamonds and squares on the plot on the right. And we also indicate how much variability it has indicated by the ellipses around the dots. Okay. So I'm not going to talk about this, but I'm going to talk about the next one. Okay, here, this is one data that I want to show. I actually used it recently in another talk, so I'm just putting it up again. It was easy to do. If you look at it, this is a study by Fleming and Johnson in 2007, and then they are looking into the production of the Schwa vowel. And there are 2 contexts in the Schwa vowel is used: the boxed rectangular, the squares, the empty squares, they represent the vowels, so the Schwa vowels that are produced in non-final context, and in the triangles are basically Schwa vowels which are produced in the final context. So in case of the triangles, what you can see is that it is on only one context the Schwa vowel is produced. In case of the squares, what you see is that they are produced in various contexts by various speakers. So as a result of that, what you can see is that the squares kind of spread all over the place from this side of the F1 to the other side of the F1 because of the contextual effect. If you look into the if you look into the final Schwas, which are the triangles, you will see that because they only occur in one place, they are not varying too much in the F2 region, but they're varying in F1 region a lot because there are too many speakers who are speaking these vowels. And by looking at the numbers on the axis, you can see that these numbers are actually like the raw numbers, the F1 and F2 frequencies we have got raw directly from the signal, and which shows the variability of the speaker. So 2 things that we see here: this kind of variation and that kind of variation. So this kind of variation, which is the red variation, is the effect of the context. The blue kind of variation is the effect of the speaker. So this is something important that we have to take into account. In part 2, I'm going to talk about analyzing vowels. I'm going to talk about what we are going to record, or what we usually record, how we segment, and how do we represent the vowel areas. So recording vowels in our cases, when we are doing our work, what we do is that we try to record both in isolation and in sentence frame, because the characteristics of vowels may change actually in these two contexts. And of course, as far as duration of vowel is concerned, of course, in isolation and sentence, there is a huge difference. Okay. So we try to produce these vowels, the speakers that we collect data from. We try to get them, produce them in a given consonantal context, like a ha and the very common context, or if possible, the other possibility is that all the possible contexts that are allowed in the language, you ask them to produce it in all possible contexts. And in our case, not in like in all cases, we try to get at least 3 iterations repeated randomly. I mean, not one after another, but at different times by each speaker. And we take multiple speakers' data, recorded data, and balance by sites. And it's difficult to get a soundproof booth everywhere, so we try to record the data in as noiseless condition as possible. So the first problem that we have after, we get the vowel data is to detect the vowel boundary. And this is the production of a vowel hit. And you can see, it is very difficult to see where the ha boundary is, where the boundary between ha and e and the and e are. So what we have to do is that we have to go into zoom into the signal here, and what we'll see is that ha is a fricative which will have aperiodic noise, where things will not keep on repeating. So as soon as things keep repeating or they become periodic, we know that it's an indication of a sonorant or a vowel in this case. So we know that wherever periodicity begins, where the signal keeps on repeating, same pattern keeps on repeating, that is probably the beginning of the vowel. Similarly, at the end of the vowel also, we see that wherever the periodicity ends is probably the end of the vowel. So we make the boundary between the vowel areas based on this periodicity. And then there are a few concerns that I don't want to discuss due to the lack of time at this point in time. So we mark the vowels like ha, e, the, as you can see here, and then a kind of program like Tract can give you a formant distribution, a formant visualization somewhat like this. As you can see, there are these red dots, and the lowest red dot series of red dots indicate that is the first formant, or F1, which indicates the height of the vowel. And the second formant, or F2, indicates the frontness or the backness of the vowel. Okay, so this is, and apart from that, you also get the information about the duration of the vowel along with it, which is very important in cases where there is a phonological difference between duration of vowels in many Indian languages, specifically spoken in South and North India. Okay, so here I come to the third part of the talk, where I talk about the formant values, removing speaker effects, and plotting with ellipses, and overlap measures and classification. These are so before I go any further, I'll give you a 15-20 seconds break, and in the meantime, I'm just going to check how am I doing with time. Okay, super. So yeah, I have about maybe 10 minutes. So I'll try to leave some time for questions too. Okay, so this is what my previous segmentation looked like for a vowel, right? So now there are two things, where do we calculate the formant of the vowel? Should we calculate throughout the E vowel, or should we calculate the middle, or what should we do? So for a long time, people believed that because the first initial parts and the final parts have a lot of co-articulatory effects from the consonant before and from the consonant after, maybe we should not take that into consideration. So for a long time, people also believed that we should only take the midpoint of the vowel for calculating the F1 and F2. So somewhat like this. However, in the recent cases, what we have noticed is that midpoint sometimes may give you spurious results. So the best method as of now is probably to take the mid 20% of the vowel and then analyze the F1 and F2 frequencies from the mid 20%. So this is also the methodology that is adopted in some of the paper that I'm going to discuss now onwards. So the second point is that, as I have pointed out to you in the previous, in this particular graph, that if you look at the plot, then you see that the final schwa varies a lot on the F1 measures, and that is because of the speaker influence, because each speaker has a different length of vocal tract depending on their own height and how big they are, etc. There are different physiological factors. As a result of that, those physiological factors are also implemented on the representation of the on the formant frequencies of the vowel. So now here is somewhere where Bapak Susanto's work and our work is different, because Bapak Susanto's work, which he has discussed right now, it is very important to find out these individual speaker-specific features. For us, as phoneticians who discover vowel systems, for us, individual differences don't matter. For us, what we want to find out is that how does the vowel sound like without this individual interferences. As a result of that, we go for some kind of vowel normalization method where we try to remove the speaker effects. So there are several methods that are there to do the speaker, remove the speaker effects, and the most useful, considered to be most useful, and something which is really popular is the Lobanov or the Z-score method of vowel normalization. This is what you do is that here you take the raw signals, raw of F1 or F2, subtract the average F1 or F2 from the raw signal, then divide it by the standard of deviation of the total average of the formant frequency. So I can talk about it more, maybe post the talk if you want to talk about it. And then as a result of that, the result of this normalization method is such that you get some positive values and some negative values, usually varying between -3 to +4 on both F1 and F2 axes. So earlier you used to get these 200, 300 numbers. Now you don't get these 200, 300 numbers. Rather you get this +1, -1, those kind of numbers. The reason being is that those numbers, that 200 and 300, had the speaker effect. Now, by removing the average, we have actually taken care of removing that speaker effect from there. And what we assume now is that we have perfect only vowel specific features. So this graph that I have showed you earlier, this already has actually, if you can notice, on F1 axis and F2 axis, they have the +1 and -1 kind of values, rather than having 200, 300 kind of values. Okay, now what happens is that now after we have calculated these values, as you know, that these values are now a lot of points of data. And it is very difficult to summarize something, because if you look at the purple dots here, you can see that some purple dots are somewhere up there on the plot, and some were on the extreme left, etc., etc. So some data are actually outliers, some things that we cannot control. So as a result of that, what we do is that we try to make a best estimate by putting a vowel ellipsis around the mean of the vowel to say how well the data fits a significant portion of what the numbers that we have. So this is once the mean is calculated, what we do is that we make a degree of confidence how much deviation is allowed in case of this vowel, in case of the mean of this particular vowel. And that we also express in terms of on the plot. As you can see in this particular plot here, what we have done is that we have plotted the vowel mean, and around that we have put an ellipsis, which is based on the deviation of the data, how much the most of the data is deviated. So that is also done with one standard deviation, which takes care of about 68% of the deviation from the mean values. So another interesting thing that happens here while looking into the vowel ellipsis is that you would notice is that these kind of features, what you'll see here is that these two categories are actually overlapping with each other. Right, you can see that EA and schwa and etc. They are kind of overlapping with each other. Now, as once we have collected the data, there is no way. It is a long process to go back to people and ask them, do you hear these two sounds differently, this one and this one differently? And that's a completely different area of phonetics. But as somebody who does a quantitative analysis or instrumental analysis of phonetics, what we'd like to do is that we'd like to measure that how much overlap is there. If we can get some matrix, or if we can get some coefficients of these overlaps, that will give us a good idea whether if there of the possibility of the people hearing these vowels separately into two categories or overlapping into one category, like as you can see in the schwa and the a case in this particular graph. So there are two methods that we have been using recently. One is the Pillai-Bartlett trace method, and the other is the SOAM method, which we'll go on to in a little bit. In the Pillai-Bartlett trace method, what happens is that it is a case kind of statistics, additional statistics that comes with the multivariate analysis of variance, which is like a multi-ANOVA kind of test. In that case, what happens is that in ANOVA you look into one factor, right? You looked at how height is determined by nutrition. But in MANOVA you can have two kind of factors, such as how height and economic condition nutrition and economic condition have effect on height, etc. So when you do this kind of MANOVA kind of analysis with two factors, in our case F1 and F2 for example, what we also get is that we also get something called a Pillai score or the Pillai-Bartlett trace. So this is considered to be very robust in the methodology to analyze the separability between two data categories. So if we have A and schwa in the previous case that we have seen, if the numbers are near zero, then you know that there is a merger. There is these two vowel categories are merging. If the number is somewhere near 1, then you know that these two are not merging and they are very distinct from each other. So depending on the distribution that we have, we'll see a number between 0 and 1. That will give us an estimate whether the two categories are separated or not separated. Here is an example that I have tried to put for you from SME's data, which is my student Lina's work, and she is working on this right now, where we have looked into the separability of different vowels. If you look into your backs, back vowels, you can see that two vowel categories are overlapping there. Two vowel categories are overlapping there, and the Pillai-Bartlett number or Pillai score is 0.02, which shows that it's almost overlapping. On the other hand, on the left, we are looking into that teal blue category and the red category, where in between where I have put the 0.64, which is almost near 1, so we know that they are well separated. Why it is not 1 completely? Because this is, again, remember the ellipsis is made on only the selected best 67% of the data. It does not show the complete amount of data, right? So this is the case of the SME's vowels. So the SWAM, or the Spectral Overlap Assessment Matrix, is something that Wasink in 2016 proposed. And then what they're doing is that they're trying to make a best fit analysis for two vowel categories. They're trying to see how much in a normally distributed set of form and frequencies for vowels, how much overlapping is happening. So that you can see in terms of percentage of overlap. So Wasink shows that, and Wasink concludes, gives some how do I say, thresholds for that too. Wasink shows that 0 to 20%, if there is overlap, then that much of overlap is not considered vowel overlap. More than 40% or equal to 40% overlap is called a complete overlap, and between 20 to 39% is a partial overlap. So this is very useful in cases where we are looking into languages, where we assume that certain varieties of the language have got some vowels merged, while some other varieties have the vowels distinct, etc. So if you do the SWAM analysis, you'll come to know about these numbers. However, remember that these numbers are can be language specific too, and in fact there are quite a few serious criticisms of Wasink's work in the same journal where this paper is published, which I have in the references in the following years. So you take this methodology with a little bit of care. So if I look into the previous case of Assimilation vowels that we have talked about, if I look into these two vowels that are in question, what we see is that this is the SWAM plot, and you can see kind of blue squares and these red circles. They are kind of overlap. So this is what SWAM has produced after analyzing the data, and it tells us that the overlap is almost 100%. So we'd also assume that in terms of perception, also probably the speakers of Assamese would not hear the difference between these two vowel categories. Haynes and Taylor 2014 has come up with an advanced version of SWAM, which is vowel overlap assessment with convex hulls. So this is the latest methodology, but I have not used that one, so I differ from talking about it at this point of time. So now we have got these vowels, we have got these measures which say that they are they are overlapping or not overlapping. Now my question, that the immediate question that comes into the mind is that can people hear the difference, right? And one way of looking into that is that doing perception tests. Perception tests are you have to do it very carefully and with a lot of preparation. So what we try to do is that we try to use some kind of machine learning in in trying to understand how this given F1 and F2 and other features, how the machine can classify these vowels into different categories. So these are statistical classifiers that we are using right now to differentiate between classes of vowels. And we can have multiple features. We can have the F1 and F2, which are common features, but we also have these other co-articulatory features such as F0. You know that F0 also differs according to the vowel differences. That is called the intrinsic F0, right? And then sometimes intensity, duration, all these factors, each vowel has its own intrinsic duration also. So all these factors actually help us in discriminating the vowel. So we can add all these different information about vowels into our classifier, and ask the classifier, can you classify these 6 vowels in a given language or not? So the one that we are using right now is called the quadratic discriminant analysis, and which is a discriminant analysis, which is mentioned in Williams and Escudero's work in 2014. I have the references at the back, and I'll be more than happy to email you regarding this. So now what we can look into is that how the combinations of features such as F1, F2 can be used in classifying the vowels. We have done this work in a language called Sora, where Luke Horo, my colleague, and us, we have collaborated together and come up with a paper on Sora vowels. As you can see, Sora vowels are pretty well distinct. They are very distinctly in different places. So you hope that people will be able to hear them well, and the classifier will be able to classify them well. So what we did is that in the classifier we put different kind of features. If you look into A here in the table, when we put the F1, the ability to discriminate is ignore the first syllable or second syllable for the time being. About 50% of the times it gets it correct. If you do F2, then it goes up to about 52. If I add both F1 and F2, which probably all of us are using in hearing vowels, the success rate goes up to about 79%. And when we add different features, like if you look into the item in G, we have used F1, F2, duration and intensity. The success is even better, about 82%. And so when we have used F1, F2, duration, intensity, and F0, as in the case in J, our ability to, the system's ability, the machine's ability to discriminate between vowel categories go up to 83.4%. So this tells you a couple of things. First of all, F1 and F2 are good enough to distinguish up to a point. But if you want to further enhance the distinction of these vowels, then you have to use these other measures such as durational information, intensity, and F0 information also to enhance the perception of or classification of vowels. So this is a good way of knowing that whether what we have seen in the graph on the left is actually corroborated by machine learning, or like a kind of a machine which tends to be like a human, in case you cannot test it with humans. So these are the things that we wanted. I wanted to discuss today. I think I have enough. Yes, I have good amount of. Oh, sorry, I'm a little bit over time and eating into Sondev's time. So I'll quickly summarize. I gave you an overview of vowel analysis and classification. You may use it in analyzing Indian language data, specifically in cases where phonological status of some vowels are doubtful. And always it is preferable that perception tests on vowels be followed up after these kind of works. And if you have a question or a comment, please feel free to email me at priyanku@gmail.com. And apart from that, we also have a Center for Linguistic Science and Technology at IIT Guwahati, where we do a lot of these kind of work, specifically quantitative analysis of linguistic features. I would like to collaborate with us. And if you have a question or if you want to come down for some work, you're welcome to come here. Thank you so much. I'll stop here.
Thank you, Priyanka, for that well-organized and well-explained lecture. It was very informative. Hope everybody enjoyed it. If anybody has any questions, you can ask now. Maybe we can take a question or two.
I'm worried that I'm eating into Somdev's time, actually. So.
Okay, and I look like there isn't any much
good afternoon.
Questions. Okay,
am I
so
audible?
Priyanka?
Yes.
Yes.
Please. Yes, please continue.
Yes, Isha Bhattacharyya, you may ask question.
Yes, good afternoon, sir. Sir, you talked about the use of Tract in the analysis. Can you also elaborate on the use of machine learning, etc., because Tract is mostly statistical. So, what about the use of machine learning in vowel analysis, etc.?
Yeah, but that is actually being done. For example, if you want to detect the boundaries of vowels, that is already there, right? However, what vowel it is, it differs a lot from language to language. Even though we have category-wise so many vowels, as you know that the German E is very different from the English E. Right, so it becomes unless you train it on that particular language, these methodologies there are works already where they are trying to automatically categorize them using machine learning, like deep neural network, etc., or some of the further technologies. But at the same time, we have to realize that many of these features in languages may be very language specific, right? And they may not be captured in machine learning, and unless you have a huge amount of data. And in most of the Indian language cases, we don't have huge amount of data, and that is the reason why we're still going for a much more pen and paper method and non machine learning methods as of now. But I would like to discuss more about it with you by email or any other means.
Okay, thank you. Sure, sir.
Okay, thank you. Thank you, Priyanka.
Yeah.
Okay, so now we'll move on to our last speaker of the day, Dr. Somdev Kar. Let me introduce Somdev Kar to you. Dr. Kar is an associate professor at the Department of Humanities and Social Sciences, Indian Institute of Technology, Europa. Prior to joining IIT Europa, he worked at the Leibniz Center for General Linguistics, Berlin, Germany, as a research associate, and at CIL Mysore as a fellow, and later as a research faculty at Qatar University, Qatar. He earned his PhD in linguistics from Eberhard Karls University of Tübingen, Germany, after completing his MA in applied linguistics from University of Hyderabad. He too has to his credit many projects sponsored by various foreign agencies like Terrasoft, Oracle, and Microsoft, all based in USA, Acapella Group, Sweden, and Zig Corporation, Canada. His research interests lie in the fields of phonetics and phonology, distributed morphology, evolutionary linguistics, and NLP. He has published a book and several research articles in internationally acclaimed journals. So I'm happy to have you here. I welcome you to deliver the lecture.
Yeah, thank you so much, Dr. Anusri. I would also like to thank Priyanku. He kind of finished right on time, although he mentioned several times he's eating my time. No, it's okay. I mean, I'm not going to really take a very long time first, but I must mention here that this presentation is going to be somewhat different compared to the two sessions that we have already went through. Okay, so am I okay? So is it now visible there?
Yes, it is.
Okay, so can you see the slides?
Yeah. Maybe you need to enlarge it.
Okay, I 2 times it just moved. Hold on a second, please. Okay. Yeah, it should be in the slideshow mode now.
Yes, it is. Good to go.
Okay, so from the topic of this presentation, you can figure out this is going to be somewhat in the theoretical direction. And compared to what Dr. Shushandu Saman and Dr. Priyanka Sharma has presented, this is going to be less in data and bit more on the theory side. So I apologize for that at the very beginning, but it is about optimality theory, which is one of the areas that I work, and I'll try to put it more of a workshop mode, what Priyanka also tried to do. So those who are attending this session, I am also guessing many of you are students, so you might have gone through some optimality theory course, or you have encountered it as part of your other phonology related research, preparation, reading. I am also guessing some of you might be from some other talk where I have presented some of these concepts before. So I apologize for that at the very beginning. It might be a little bit repetition for you. So anyway, let me start with this slide, which is not really related to optimality theory or OT, but this is how we all, perhaps we all started learning phonology or the phonological rules. So this is the typical generative phonology model where the conspiracy theory works, right? So we try to look from, say, A to B, change in the X and Y environment, or A to C change in X to Y environment, or it gets deleted in X to Y environment, etc. And this is completely something where optimality theory differs. Okay. So in optimality theory, we are not looking into this kind of phonological changes. What we do, this is a bit of visual representation of it, but believe me, OT tableaus look very different from this. But this is where, like, we all can see an input like this, you know, ends up in an output like this through several constraints, and these are the possibilities that are coming from this. And so this is a bit of complex looking at the beginning, but let me try to explain it. By the way, this was not prepared by me, but one of my former students, Dr. Pankaj Devedi, who is presently at CIAL Mysore. And thanks to him, this was nicely done by him, so I took the liberty of using it here. So since this topic is focusing on OT, but the more or less the emergence of OT among several other phonological theories. So let us very quickly look at what are the other theories that ruled, or they are still very much in the use in phonology research. We can always go back to the Paninian framework, that is the Ashtadhyayi, and which was as old as 4th century BC. And Panini has given us some very interesting and powerful sutram, and that is a whole different world if we try to look at it from present day phonology theories. But if we come to the modern time, in the sense 20th century, Prague school gave us some wonderful theories at that point, because that was also kind of starting point of the the phonology research that we do in today's time, like Nikolai Trubetskoy or Roman Jakobson and some others. But then again, if we jump, that was early 20th century, then we jump to the generative phonology, the conspiracy theory that we've just seen. That was in 1960s. It started with sound patterns of English of Chomsky and Halley. And then there is a big paradigm shift again by John Goldsmith. In his thesis, he presented autosegmental phonology that was somewhat different from the earlier studies. And then again, we came back to the generative model in terms of government phonology by Jonathan Kay, Jean Lowenstein, Monique Sarret, and that was in 80s. Okay, then comes what is there in today's thing, the optimality theory, which was presented by Alan Prince and Paul Smolensky. But then there are many others who added significantly in this theory. We'll be, of course, focusing on this, but very quickly, let me also tell that evolutionary phonology is also something which is coming in the picture, and which I would not say another advanced theory or so, but this is more of a different thing, but it is a recent one. So Juliet Blavin's work, Senichi Tanaka's work, they are coming in the picture and people are getting more and more interested. This is more of post-2000 thing. Okay, now to start with OT, I would first like to tell what it is about and who are the people behind it. So OT was developed in the 1990s. In particular, it started with a scientific report by Alan Prince and Paul Smolensky. And many people actually call it a connexionist theory because it has a certain amount of this connexionist model. And if we actually look back, it has roots in neural network research, which is quite interesting in today's time because of phonology and neural networking research. Yes, there are some works going on, but that was the beginning of it, you can say. Of course, we should not forget that it has certain connection to the harmonic grammar, which was also developed in the 1990s, and at least you can see Smolensky was part of it. Okay, so what actually happens in OT? Why it differs from those rule-based model? So if we look at some of the points taken here from Reintager's book, look at these points. Here, what happens? The surface forms, like when we speak, the surface form, they are basically in OT looked at the reflection of resolution of conflicts between competing constraints. Now, what it basically means that for each and every surface form, there are more than one competing candidates. So the candidates are like each of them are coming out of the base form, the underlying form, and they're competing among each other to be the surface form. And there are several constraints which are putting some obstacles in front of these constraints, and the best one which is coming out of this conflict is marked as the optimal candidate, and that is the actual surface form that we speak. And so this surface form, which is the optimal form, so if it incurs the least serious violation of all these constraint, fighting, so the least serious violation becomes the optimal form. And these constraints are actually universal constraints. It is not like for language A, there is a set of constraints, and language B has a separate different set of constraints. No, it is not like that. But for these set of universal constraints, which can be used and applied in any languages in the world, the ranking will differ. So which constraint is more fatal, which is less fatal, is dependent on the ranking. Now, if we look at the typical tableau which looks like somewhat like this. So here, there are different constraints. So this is the highest ranking constraint, which will be more fatal. And this thing make the difference. Now, this is my one of my favorite examples I always give whenever there are some students involved. So this is like a couple of students in a hostel. Okay, so let us try to understand it through this mode. So a couple of students, the students on the left side in in this black dress, she has certain rules. In a hostel living, in general in life, she has certain rules. The rules are like, don't stay up late. Whereas on the right side, the second student, she doesn't have rules as such, but she has certain preferences. Preferences like, well, sleep well, party with friends. Both are preferences. Now, with this two setup, if there is a situation arises, some friends inform, well, there's some birthday party there tonight, kind of midnight party. Now, what will happen about their decision? So the first one, who goes by rules, so she checks her rules, and the only rule that I can see here is that up late. So the midnight party, well, it is kind of cancelled. When it comes to the second student, she doesn't have rules, remember? So she checks her preferences. So there are two preferences. So she ranks the preferences. Which one should rule here? Which one should not rule here in that sense? Rule of the first student. Which one will get preference here? So eventually, you can see this is getting higher preference. So this one, so stay back and sleep, getting higher preference for her. So sleeping is preferred, and since there is no party for her. Now, what I'm trying to say here is that there might be two different ways to reach the same conclusion, right? The conclusion is same, they're not going to the party, but the method is different. So let us not go into that thought that OT does something very different for the phonological outputs. No, the results are more or less the same in most of the cases, and it is about the analysis, it is about the way, it is about the method that we are using to reach that. So here in the second case, we are going by the ranking of the preferences rather than any rules, whereas in the first case there are rules. No, I'm not saying this is a good and that is bad or so. These are just two different ways of looking at it. Okay, so there is no change in the result as such. Now here I will not explain each of them in detail. Okay, so these are four major components in OT: the lexicon, which is the lexical representation of this, are the underlying forms, the input that goes in OT analysis. Then Gen is a hypothetical generator which creates a lot of candidates, possible outputs from the lexicon. Eval chooses the optimal candidate. It does the evaluation. Again, this is hypothetical. And these cons are there to help the constraints which are giving us the resistance to all these candidates that Gen generated. Okay, so cons poses all the hurdles to them. So if we look at very quickly, do I have no, not this, sorry. First, let us very quickly look at what kind of constraints are there. So there are two kinds of constraints: the faithfulness constraints and the markedness constraints. So the faithfulness constraints, these constraints like that there should be some similarity between input and output. Okay, so let's say in English, the very common and perhaps favorite example of our phonology is that thin thing becomes Spain. So there, for Indians, at least who not only for Indians, all the language speakers in India or outside, where this per and fur are two distinct phonemes. For them, this is like one input is giving a different output, so that input is not faithful. So the output, sorry, it is the output is not faithful to the input. The output changes from the input, right? So here, this faithfulness constraint will be violated. Whereas markedness constraints, they enforce well-formedness of the output itself. So it has nothing to do with the input. It just bothers about the output. So if you have a markedness constraint that says the output should look like this, the output should look like, say, ABC, and it just bothers about that. Even if the input is XYZ from ABC, from this input XYZ to output OBC, markedness constraint could not bother about it if the constraint required the output should have ABC. So it will be satisfied in that case. Okay, so these are the two ones. So just to quickly put it in the context, the faithfulness constraints, it tallies between these two, and if the output is not faithful to the input, it marks a violation. Whereas markedness constraints, that directly gets applied to the output irrespective of what is there in the input. Okay, so these are some very common markedness constraint, like based on typological data, that like obstruents must be voiced. So many languages have voiced obstruents, and then no front rounded vowels or no nasal vowels, or words must start on a consonant, etc. So generally the CV structure is more preferred. So these are the markedness constraints, whereas the faithfulness constraints are like there should not be any deletion, there should not be any insertion between input and output, then alignment should be maintained, there should not be any change in the alignment, and so on. Now I'll skip this one. This is like going through how the constraints filter. Again, this was done by Pankaj, and I'm not using it. But I want to take this quick example from a very common phenomenon we all have seen while learning phonology, particularly the allomorphic part. Like the example is cat, English, cat. Okay, so what happens in the pluralization, the default plural form S gets added, which is realized as actually the. And in case of cat to cats, you see this hand mark says that this is the optimal candidate. So we have 1, 2, 3, 4, 5 constraints, like star shape that says that no 2 consecutive sibilant sounds should be there. Then max IO, again, you remember here max IO was introduced. Max IO says no deletion, and deep IO says no insertion. So when you go to the max IO, here it says that there should not be any deletion. So like here, you see in cat, the is missing. So there it gets 1 star, which is 1 violation. Like that, there are several other violations in DeepIO. DeepIO says that no insertion should be there. So in the catties, this I got inserted, so it is a violation. Agree voice says that 2 consecutive sounds should agree in voicing. IGNTU says that the input and output should have voicing, they should be identical. Now, the interesting thing is all these were ranked in certain order, and we have ran we ran all the candidates, like this is 1, 2, 3, 4 candidates to each of them, and they got violation. The fatal ones, so we check from left to right, the fatal ones got an exclamation mark, and they run out of the competition. And at the end, this is the second candidate, cats, has 1 violation, but this is the least fatal violation because it is the lowest rank constraint. So it doesn't have any other violation here, 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 here. So that is how it worked. Now, interestingly, if you go to dogs, the second example, dogs, here the Z, that example with Z is the winning one. But here, the cats, that Z one was not the winning one. And interestingly, again, look at the ranking remain the same. So each constraint here and here, they have the same ranking. So this is basically telling us another thing. We cannot simply even if we want, we cannot change the ranking inside the same language. The ranking is very sacrosanct. Ranking within the language is actually the way, the path to the grammar of that language. So it should not be changed. Okay, but for another language, the same constraint may form a different ranking, and it gives you different output. It gives you different optimal candidate, right? So these are called tableau, and these give us two different output for cat plus S and dog plus S. In the first case, it is cats, the voiceless one, the voiceless plural sound ending, and in the second case, it is dogs, which is the voiced plural sound ending. And there could be a third one, which will give us outputs like churches, bridges, judges, kind of example, horses. Same ranking will be there, same tableau. Okay, now I also thought I will to give some example from Indian languages how this works. So I took few examples from Tanmay Bhattacharya's 2000 work, like this is on voicing agreement in Bengali. So these are from Bangla. The examples are like when we have, this is in colloquial Bangla. So from jak to jakke, actually, eventually, this ka and followed by this ga becomes ga ga, not ka ga. So this is not ka ga, but ga ga. Now, and then there are several other examples like satgun becomes sadgun, satbhab becomes sadbhab, satjan becomes sajjan, and so on. So what is happening here in many languages, like including in Sanskrit, Polish, Dutch, Catalan, many languages, the voicing assimilation, it takes place in obstruent clusters with the word final neutralizations. This is from Linda Lombardi's 1991. So in Bangla, what happens? Neither a voiced obstruent is ever followed by a voiceless obstruent, nor is voiceless obstruent followed by a voiced one. So eventually what happens is the voicing in the coda is adjusted to the voicing of the following onset. So what we do here, we have taken three constraints, none of them are my own constraints, they were already used in Beckman's work, Lombardi's work, and Ethan Mester's work in Japanese. And that example is taken as in terms of preservation of voicing. So unlike that merging, oh sorry, I missed that, I did not put that tableau of that example. But here, where it is being preserved, so this g and the is being preserved. So these three constraints, they are interacting with each other, and we have for mugdha, we have one is with ga dha cluster, one is ka tha cluster, both were voiceless, devoiced, and one is voiceless followed by voiced. And you see the second and third candidate, this one and this one, they were ruled out because of higher ranked constraint violations. And this one, even though it has two violations, it actually is the winning one because of the lowest rank of VOP. VOP is a constraint that says that no obstruents must be voiced. So this was ranked low in Bangla. Now here comes the neutralization case, that Jagge case. So the same constraints were also maintained here. See, agree voice, identifier voice, and VOP. Here also we have agree voice, identifier voice, and VOP. We added one more, but it is with a dotted line, which means this is not, these two are not in crucial ranking. Here also, now here that Jagge is winning, not that Gaga cluster. Sorry, the Gaga cluster is winning, not the this one, right? Because of this higher ranked violation here, and here there is another additional violation which is not here. And similarly, we can also look at the final devoicing, which is also very common across languages. Like in Dutch, we have hande, like hand in plural, whereas in singular it is hunt with voiceless sound. Compare these two. Bet compared to bedan, which is plural. In German, rund, which is round, to runde or so. Or lob to lobes. So here, what happens when we look at final devoicing in Bengali, in Bangla, this devoicing does not happen in a word medially, be it the syllable ending at the coda position, but in the first syllable of the in the coda of the first syllable, but still it does not devoice. Although this one is actually indicating that in the same ranking it should be, right? So in Bengali, actually the final devoicing happens only at the end of the word and not in the middle of the word. So it remains actually job. This should be the actual example where it wins. Okay. So now actually there could be several other examples, several other phonological phenomena we can discuss, but here there is always some time constraints. So let me very quickly finish the talk by mentioning few advantages and disadvantages, because again, like any other theories, optimality theory is also not a flawless one. It has its own demerits, but let us first look at the advantages. So in OT, one of the advantages is the prediction of the emergence of the unmarked. So all languages have certain unmarked forms, unmarked outputs, etc. And this markedness constraint that is frequently violated in a language, it still affects the output. So we can decide which output should be there, and we can rank the markedness constraint accordingly. Then the homogeneity of the target or heterogeneity of the process is also there, where there is a markedness constraint against the target, but whether or how the target is repaired depends on certain interaction with the other constraint. These, well, there are some other advantages, but these two I thought maybe worth mentioning here. Well, there are some disadvantages. Disadvantages are also not very small in nature, or they're not so small. So one is the biggest criticism against OT is that it is unable to capture the most opacity. In the rule-based model, you can always see a latter rule either eliminates the structure that caused some earlier rule that was applied, or creates a structure that would have caused an earlier rule to apply. So like that rule ordering, that bleeding relation, the feeding relation, you may remember those. So in OT, those things are absolutely, they're not there. Here, the entire approach is the constraint-based approach, where there is nothing like the earlier rule should be applied first and then the latter rule comes. Here, it is like all the constraints are applying at a time. But well, we can always rank them. But that does not really rule out the
Yes, sir. It is visible now. Yeah.
Okay. So there were certain gemination cases that that was like here you can see from Sanskrit putra to in Bengali it becomes putro. Now this ta is getting geminated here, and the
Yeah.
gemination is understood here as sorry, as just a second. This sharing of one of the coders as the concept for the following, following syllable. So here you can see what kind of constraints that are used here to analyze that. Okay. So one is the syllable contact constraint,
Yeah.
and other is no gem. But no gem has to be very low rank because otherwise the gemination won't happen at all. Okay.
Okay.
So no gem is the kind of the bad constraint here, where we allow the gemination to happen. So syllable contact is the one which is actually blocking your example, that is pa ka. It should be the one that will block it, because syllable contact says that, so look at here, it is below here, sonority must not rise across syllable boundaries. So okay, no, so here it is not really rising, so we should use one of the other ones.
Yes,
Okay,
sir.
so max IOC or max IOV, just look at them if they're working there. Okay, and of course there could be some other example where here actually all the examples where there were two consecutive consonants. So without the consecutive consonants, I have to look at some other examples. Can you please be in touch with me through email? I can
Yeah.
say.
Sure, sir. Sure, sir. Sir, for all the universal constraints, which book should I follow, sir?
See the constraints, those which are already in use. Well, they are recorded in many other. I mean, I think in Kaga's book there is quite a lot of them already
Sir,
recorded.
in Kaga book, that SWP is not mentioned, sir. Stress to weight
That
principle.
might be a
SWP is mentioned, but not SWP.
Of course, that might be better. But again, this is an ever-growing list, so it is not possible to tell that this book has all of them.
Okay,
But well,
sir.
try to look at some recent work, and if I find, I can always share with you. Please be in touch.
Yeah. Thank you, sir. Thank you, sir.
Okay, thank you, Arpita. Thank you, Somdev, for that interesting session. I would now like to invite Dr. Pramod Kumar, Assistant Professor, Department of Linguistics and CSTLers, IGNTU, for the vote of thanks.
It is my privilege to present vote of thanks in this international webinar. First of all, I would like to express our gratitude to our Honorable Vice Chancellor, Professor Sri Prakash Muni Tripathi. His continuous support and encouragement promotes us to excel in academic activities in the university. We are really thankful to you, sir. Next, I would like to express my heartfelt thanks to our invited speaker, Dr. Shushandu Saman, Hague Center for Studies in Linguistics, Bandar Lampung University, Indonesia, Dr. Priyanka Sharma, Department of Humanities and Social Sciences, IIT Guwahati, Dr. Somdev Kar, Department of Humanities and Social Sciences, IIT Ropar. We are really grateful to all of you, sir, for accepting our invitation to enlighten us with your expertise. I hope everyone has got benefited from. We are thankful to all of you, sir. I am also thankful to our Dean, Professor Prasanna Sama, for his continuous support and encouragement. I also express my gratitude to our colleagues in Faculty of Travel Studies, to name some, Dr. G.S. Mahapatra, Dr. Krishnan, Mr. Hardeep Singh. I express my heartfelt thanks to the convener of this webinar for her effort to organize the international webinar on recent topics of interest in phonetics and phonology. At last but not the least, I express my gratitude to the participants of this webinar for their presence and having patience to listen to our speakers. Thank you.
Thank you, sir. Thank you, everyone. Thank you, sir. I would personally like to thank Dr. Pramod Kumar for your guidance and continuous support for the successful conduct of the webinar. Thank you, everyone, and we appreciate you being here. Thank you.